Hey everyone, welcome back to another physics past paper video. Today we're going to talk about paper 2 from the May-June 2024 series, and the variant would be 22. So let's jump into the paper. Question number 1. The list below shows some SI quantities. Underline the quantity that is not an SI base quantity. So base quantities include length, mass, time, current, temperature, amount of substance, and luminous intensity. So what do we have over here that is not? So current, length, and time are base, charge is not. So just simply underline it. A square solar panel with sides of length 1300 mm is shown in figure 1.1. The light is incident normally on the solar panel. The power of the light incident on the solar panel is 750 watt. Calculate the intensity of the light. Now we know the intensity is power incident over the perpendicular area. So power is straightforward, that is already given 750, but the area given to us is given in, the dimensions for that are given in millimeters, so we have to convert it into meters. So 1.3 squared. So power over area, that's basically what that is. So 750 divided by 1.3 whole squared, you get 443.8. So we can round it to 440. Okay. The percentage uncertainty in the incident power is plus minus 3%. The uncertainty in length of each side is 5 millimeters. Calculate the percentage uncertainty in the intensity of the light. Okay. So for the power we already have in percent. For length we need percentage uncertainty. So delta L over L. That is equal to 5 over 1300, 5 millimeter, 1300 millimeter, and then times by 100%. So 0 gets cancelled, so 5 divided by 13 is 5 over 13. Let's keep it exact because we need to use it to get a further answer. So for the percentage uncertainty in the intensity, we have 3% plus, what do we have? Oh yeah, sorry, so area is length squared, so 2 times by 5 over 13%. So 3 plus 10 divided by 13, 3 plus 2 times by 5, 10 divided by 13, that is 49 over 13, 3.8%. Right, okay. The useful power output of the solar panel is 160 watt. Calculate the percentage efficiency of the solar panel. So we know that the efficiency is the useful power output over power input, or total power input. So this is 160 divided by 750 watt. Right, okay. So 16 divided by 75, that is 0.213, and we need to give this in percentage, so 21.2%. 21% would be fine. Another square solar panel is placed so that the light of same intensity is incident normally on it. The new panel has shorter sides than the original panel. The new panel has the same power output as the original panel. State and explain whether the efficiency of the new panel is greater than, less than, or same as the efficiency of the original panel. Okay, so we know that the intensity power incident is intensity times by cross-sectional area, the perpendicular area, right? So just rearranging intensity. So the power intensity, light of same intensity is used. So intensity is constant. So power incident would be proportional to area, right? Now, the new panel has shorter sides, so that means if the cross-section area has been reduced, the power input would have reduced. However, for the efficiency, power output is same, but power input has been reduced. So that must mean that the power efficiency has increased. So that's what we just simply have to write. The efficiency, so first, power incident on solar panel is proportional to a perpendicular area where intensity is constant. In this case, is same, or you can use the word constant. New panel has shorter sides, therefore smaller area. So power input or power incident on it would be lower. However, efficiency is inversely proportional . You can also say that efficiency is the ratio of power output to power input. So if power input has reduced, power efficiency has reduced. So instead of this, efficiency is ratio of power output to power input, where power input is same. Power input is reduced. Therefore, new efficiency is greater. So new panel efficiency is greater than original panel. Actually, it should be than that of original panel. Now you can shorten this a little bit, keep and just retain the key points. However, this is the explanation. Alright, so this is question number 1. On to question number 2. A skydiver jumps from an aircraft at time t is equal to 0 and falls vertically downwards. The variation with t of her velocity v is shown in figure 2.1. Okay. Using figure 2.1, state the terminal velocity of the skydiver. Terminal already means the final, the end velocity. That means where it has become constant. So you see, this is 39. So 39 meters per second. By drawing a suitable line on figure 2.1, determine the acceleration of the skydiver at time t is equal to 9 seconds. Now 9 seconds is where, so by the suitable line they are asking about a tangent line. So this is your 9, okay, and this is the point where. Now what we need is a ruler. Okay, never mind. We can try. No. Oops, no. Let's adjust it. Yep. Slightly I think this would be sufficient. Slightly more. Right. Okay. Let's see where this line crosses, the points where it crosses. So one point we already know is this one, because that's where the tangent is crossing. We need just one more point, and this is this one. Okay, so we have points 9 and 35. The other one is 5 and 31. Okay, so we need just a tangent line, so we need a gradient. So acceleration is gradient of the tangent. So we have 35 minus 31 and 9 minus 5. So this is basically almost 4. So 4 divided by 4, 1 meters per second squared. Yeah. 9 and 35, 5 and 31. Right, okay. Alright, moving on. The mass of the skydiver and her equipment is 68 kg. The upthrust on the skydiver is negligible. After reaching the terminal velocity, skydiver opens her parachute at time t1. A total drag force of 1800 Newton acts on the skydiver. Determine the magnitude and direction of the acceleration of the skydiver at time t1. So this is when she opens her parachute at time t1. Okay, so it is already at terminal velocity. So weight acting downwards, the drag force Fd, let's call it, acts upwards. So weight minus Fd equals to 0 because acceleration is 0. Oh wait, no, sorry. Wait. We forgot to, no. It's after the time t1, sorry, my bad. So after the time 1, after time t1, that's what the force would be, because when you do 68 times by 9.81 before the parachute, it would have been this. Right, okay. Now that we know, okay. So, weight minus Fd is equal to Ma, mg minus 1800 equals to Ma. So m is 68 times by 9.81 minus 1800 equals to 68 times by A. So therefore A would be 68 times by 9.81 minus 1800 and divided by 68. So minus 16.66. So we can say 17. Acceleration is 17, but direction would be upwards, because this means that this is deceleration. Okay. The parachute is fully open at time t2. After the time at a later time t3, skydiver reaches a constant velocity of 5.7 meters per second. Describe and explain the variation with time of the magnitude of her acceleration between time t2 and time t3. So when it is fully open, the graph actually is going, this is terminal velocity, then it suddenly drops, and then it would basically start going this way. It will start going this way again. It will quickly achieve terminal velocity again. So basically that's what we need to show, that this is, for example, where T2 is, and this is where the T1 was. So after T2, and this is, let's say, T3, we need to show the variation between them. So at this point, we already know that it is the speed is decreasing. So speed is decreasing after time t2, which causes drag force to decrease as well. After some time before T3, just before T3, actually it is at a later time, after some time at T3, drag force balances weight, reducing acceleration to 0. Oh, sorry, we could actually write over here that this causes a decrease, this causes acceleration to decrease, right? Because you see, it's the difference between drag force and weight, as it depends on, or as it is proportional to difference between drag force and weight. Right. After some time at T3, drag force balances weight, reducing acceleration to 0. And that's it, right? Calculate the change in momentum of the skydiver between time t1 and t3. Change in momentum. Right, so at time t3 velocity is 5.7, but at time t1, what is the velocity at time? Okay, so after reaching terminal velocity, that was 35. Right, okay. So change in momentum would be mass. Since the momentum before was greater, so 35 minus 5.7. Sorry, no, 35 or 39? 35 or 39? 39, sorry. Yes. Right, okay. So 68 times by 39 minus 5.7, which is 2264.4. Final answer can be written as 2300. Alright, this was this question. Let's move on to the next one. Question number 3. Lightning occurs when charge builds up in the atmosphere, creating a potential difference between the ground and the atmosphere. During a lightning strike, there is an average current of 3.3 10 raised to the power 4 amps for a time of this. Okay. Calculate the charge transferred during the lightning strike. So basically Q is equal to IT. So I is 3.3 10 raised to the power 4. Time is 2.6 10 raised to the power minus 5. So 3.3 times by 2.6 times by 10 raised to the power 4 minus 5, which is 0.858, just to make sure that we have it correct. 10 raised to the power 4 IT 10 raised to the power minus 5, right? So 0.86 we can say. The potential difference between the ground and the atmosphere is 3 10 raised to the power 7 volts. Calculate the average power in gigawatt transferred during the lightning strike. So power is VI. So potential difference is 3 10 raised to the power 7. I is 3.3 10 raised to the power 4. So 3 times by 3.3 times by 10 raised to the power 7 plus 4, which is 11. Now we need this in gigawatts. So we just simply divide this number. Giga is 9, so 10 raised to the power 9, we get 990. And this is already in two significant figures, so that's fine for us. Okay. A lightning rod is attached to a tall building to conduct charge safely to the ground. The lightning rod is modeled as a uniform cylindrical copper cable of total length 95 meters that runs from the ground to the top of the building. Okay. The resistance of the lightning rod is 9.6 ohm. The resistivity of copper is this. Determine the radius of the lightning rod. Okay, so we know that resistance is rho L over A, and A is pi r squared. R squared is what we need at the first. So first we make r squared the subject. You would have rho L pi r. Resistivity is 1.7 10 raised to the power minus 8. Length is length is 95 meters, right? Yeah, 95 meters. Pi, and resistance is 9.6. So therefore this would be square root of 1.7 times by 95 divided by pi divided by 9.6 times by 10 raised to power minus 8 square root would be 0.000231. So in standard form, 1, 2, 3, 4. Right. Okay. The radius of the copper lightning rod is doubled with no change to its length. State the effect of this change on the resistance of the lightning rod. Okay. So resistance is inversely proportional to R squared, as we have seen this over here. So if the radius is doubled, if this is it's 2R, the resistance would be, you see, it would become 1 over 4R squared. So basically the resistance would be reduced to quarter of its original value. So resistance would be reduced to 1/4 of its original value. Okay, alright. We can actually state the value also, 9.6 divided by 4. A section of the lightning rod of length 0.12 meters is removed for testing. A tensile stress of 1.9, 10 raised to power 6 pascals is applied. Section of the rod obeys Hooke's law, basically, which means that force is proportional to extension. Young modulus of the copper is this. Calculate the extension of the section. Okay, so we know Young modulus formula, that is FLAX. So X would be FLAE. Right, so force is, no, we have force over area. Force over area we have. So basically, this part we have, right? So we have 1.9, 10 raised to power 6, original length 0.12 meters, divided by Young modulus, which is 1.3, 10 raised to power 11. So 1.9 times by 0.12 divided by 1.3 times by 10 raised to power 6 minus 11. This gives us 1.7, 1.8, 10 raised to power minus 6 meters extension. So 1.8, 10 raised to power 6. Right, okay. This question is over. On to the next question. Question number 4. A pinball machine uses a spring to launch a small metal ball of mass 4.5, 10 raised to power minus 2 kg up a ramp. The spring is compressed by 8, 10 raised to power minus 2 meters and held in equilibrium as shown in figure 4.1. Right. Okay. The ramp is at an angle of 15 degrees to the horizontal. Spring obeys Hooke's law and has a spring constant of 39 Newton per meter. Calculate the elastic potential energy in the compressed spring. So EP is half kx squared. So half 29, and extension or the deformation is this thing, 8, 10 raised to power minus 2. Whole squared. So this would be 0.5 times by 29. 8 squared is 64. and that would be 10 raised to the power minus 4. We have 9.28 10 raised to the power minus 2 joules. Right, okay. 9.3 10 raised to the power minus 2 joules. The spring is released and it expands quickly back to its original length. Calculate the increase in gravitational potential energy of the ball when the spring returns to its original length. Okay, so the change in length over here is the same, 8 10 raised to the power minus 2. However, the change in gravitational potential energy is actually coming from this particular change in height. So we find out the delta H first. So change in height is 8 10 raised to the power minus 2 sine of 15 degrees. So 8 10 raised to the power minus 2 times by sine of 15 degrees. This is this value, 2.07 10 raised to the power minus 2 meters. So EP is equal to mg delta H. So mass is 4.5 10 raised to the power minus 2 times by 9.81 times by 2.07 10 raised to the power minus 2. So this value times by 4.5 times by 9.81 times by 10 raised to the power minus 2, we get 9.14 10 raised to the power minus 3. So this is 9.1 10 raised to the power minus 3 joules. Okay. The ball leaves the spring when spring reaches its original length. Assume that all the elastic potential energy of the spring is transferred to the ball. Calculate the speed of the ball as it leaves the spring. Okay, so you see the total elastic potential energy, some of it is changed into increase in gravitational potential energy, and some of it is converted into kinetic energy. So change in elastic potential energy equals to change in gravitational potential energy plus change in kinetic energy. So we basically need to know what changes kinetic energy is, delta EK. So delta EK would be 9.3 minus 9.1 10 raised to the power minus 3 joules. So that is basically 0.2. No, wait. This is 10 raised to the power minus 2. Sorry. Oh, okay. Alright. So 10 raised to the power minus 2 minus 9.1 10 raised to the power minus 3. Right, okay. So 9.3 times by 10 raised to the power minus 2 minus 9.1 10 raised to the power minus 3. We get a 8.39 10 raised to the power minus 2 joules. Okay, now delta EK, this is also equal to half mv squared. So therefore v squared would be 2 times by EK change divided by mass, which is 4.5 10 raised to the power minus 2. Right, okay, so we already have this. So 2 times by answer divided by 4.5 times by 100. So V would be 1.9. That's it. Okay. The ball comes to rest on a horizontal trapdoor of a negligible mass at a distance d from its pivot. Okay, as a force F acts vertically downwards at a distance 2 cm from the pivot, as shown 4.2. Trapdoor is in equilibrium when F is 1.7. Calculate D. So it comes to rest. That means velocity is now 0. So the mass was, what was the mass again? 4.5 10 raised to the power minus 2 mg basically. So sum of moments is equal to 0. So 4.5 times by 10 raised to the power minus 2 times by 9.81 times by D equals to 1.7. Since we need D in meters, we need to convert this into meters also. So 1.7 to 10 raised to the power minus 2. So as you can see, minus 2 get cancelled, just to make sure that that's what we had over here. Right. Okay, so D would be 1.7 times by 2 divided by 4.5 times by 9.81. So 1.7 times by 2 divided by 4.5 times by 9.81. This would be 7.702. So 7.7 would be adequate meters. Right, okay. Force F is decreased from 1.7 newtons. State the direction of the resultant moment about the pivot on the trapdoor. So force F is decreased now, so the moment would be clockwise. So clockwise. Right, okay. So that's it for this question. Let's move on to the next. Question number 5. State Kirchhoff's second law. So it is straightforward. So in a closed loop, the algebraic sum of EMFs is equal to sum of EMFs and sum of potential differences is 0. Right, okay. A battery of electromotive force EMF 9 volts in negligible internal resistance is connected in series with the variable resistor X and thermistor Y. Figure 5.2 shows the relationship between temperature and resistance for the thermistor. The current in the circuit is 1.1 10 raised to the power minus 2. Potential difference across Y is 4 volts, so Y is the thermistor. Okay. Calculate the resistance of X. Okay, so if the potential difference across the thermistor is 4 volts, so that must mean that the potential difference across X would be 5 volts, right? Simple potential division. So the current flowing through this is this, potential difference is this, so R would be V over I, potential difference is 5, and the current flowing through this is 1.1, 10 raised to the power minus 2, so 5 divided by 1.1 times by 100, this is 550 ohms. The temperature of Y is changed to 190 degrees Celsius. The resistance of X remains unchanged. Determine the new potential difference across Y. Right, okay. So 190 they said? Right. Okay. So 190, the resistance would become somewhere over here. Sorry, resistance would be 25. Right. So resistance would become 25. Right. Okay. So now the potential divider formula. So V cross Y would be 25. 25 plus 550 times by 9 volts. Right. So 25 times by 9 divided by 575, which is 9 over 23, 0.391 volts, so we can write it as 0.4 volts. The resistance of X is increased. The temperature Y remains at 190 degrees Celsius. By reference to the current in the circuit, state and explain the effect of this change, if any, on the potential difference across Y. Okay, so basically what's happening is the ratio of resistance X to resistance Y is changing, right? So the ratio is now increased, right? So the ratio of Rx to Ry has increased. So which must mean that the potential difference across Y would decrease. Now we need to make sense of it. Right, okay. So due to increase in resistance of X, the net resistance of circuit increases, causing a decrease in current through the circuit, right? Now the potential difference, so due to this, right, I don't know what's wrong with it. Okay, so the potential difference across Y, which is proportional to current, would therefore decrease as there is less current flowing through it. As there is less current flowing through Y, you can also say that the ratio of the potential difference. Wait a second. We just needed Y, so I think that's fine. Yeah. So 3 points done. All right. So this was this question. Let's move on to the question number 6. Light of a single frequency is incident normally on a diffraction grating. An interference pattern of the bright and dark fringes forms on a semicircular screen as shown in figure 6.1. Light has wavelength 520 nanometers. Separation of the lines in the grating is this. So this is your D, this is your wavelength. Determine the total number of bright fringes formed on the screen. Now remember, it's 2n plus 1, where n is where sine theta is 1. So we have n lambda is equal to d sine theta. So sine theta is 1. because theta we are assuming 90 degrees, because we want to find out where order on each side would be at when angle becomes 90 degrees. So n on one side would be d over lambda. D is 3.8, 10 raised to the power minus 6. Lambda is 520 nanometers, so convert it into meters. So 3.8 divided by 520 times by 10 raised to the power minus 6 plus 9. 7 orders. And lambda and d sine theta, right? Okay. So you have 7.3. So total orders would be 2n plus 1. 2 times by 7 plus 1, so that is 15 orders seen on this. The light is replaced with red light of a single frequency. State whether the frequency of the red light is greater than, less than, or same as the frequency of the original light. Right, so we know this visible spectrum sequence, and we know the wavelengths also. So this starts with 400, 450, 500, 520, 550, 600, 650, 700. So 520 is somewhere in between. Red light of a particular frequency would be around 700. So frequency. So this is the order of the wavelength. Order of frequency would be lower. So frequency of red light is lower. Then original light. Right, okay. State and explain the effect of this change on the number of bright fringes formed on the screen. Calculation is not required. Okay. So we said that total number of fringes was 2n plus 1, where n was d over lambda. So if lambda has increased, number of total bright fringes would be decreased. So number of orders visible on each side of 0th order is inversely proportional to wavelength, since wavelength of red light is greater than 520 nanometers, number of orders visible number of orders on each side, and hence the total orders visible, or total bright fringes visible, will be lower. That's it. And that's question number 6. Let's move on to question number 7 and the last question. Question number 7. A particle Q and particle R are each composed of one quark and one anti-quark. So basically, mesons. State the name of class group of particles that includes Q and R. Mesons. Q has a charge of -1e, where E is an elementary charge. R has charge 0. Complete table 7.1 to show a possible second quark in each of Q and R. Okay, so remember the table. Up, charm, and top have charge plus 2/3 E. Down, strange, bottom have charge minus 1/3 E. Anti-up, anti-charm, anti-top will have minus 2/3 E. And anti-down, anti-strange, anti-bottom will have plus 1/3 E. So Q has charge -1e. It has strange first, which is -1,3e, and we need it to make -1e. So basically we need -2/3 E to make it into -1e. So we can put anything from this group. Now we have anti-up. So for R, you have anti-up minus 2/3 E. And now we need 0. So basically we need another 2/3 E but positive. So that means from anything from up, charm, top. Right? Right. And that's about it for this paper. I hope you liked the explanations. If you have any questions, feel free to reach out. If you would like us to do any specific paper, also please request it in the comments. I would love to hear your feedback. Also, if you have any suggestions, feel free to reach out using the WhatsApp or email given in the link tree. If you like this video, give it a thumbs up, subscribe to our channel, and turn on the notifications for future updates or future papers. And see you in the next video. Bye bye.